This is Sudheer, working as an assistant professor at Department of Civil Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the series of lectures for Fluid Mechanics course. Today, I am going to discuss about Introduction to Dimensional Analysis, which is a very interesting and easy topic for solving the problems, for understanding the concepts. Now, let us go ahead with the concepts of the dimensional analysis and applications where it can be applied. So, this dimensional analysis is a pure mathematical technique which is helpful for establishing the relation between the given quantities which are either unknown or known parameters by considering their dimensions. So, that's why it is called as a dimensional analysis. And where it is useful, this is helpful particularly in experimental work. If at all, if we don't know the relation between the two unknown parameters or more than two unknown parameters or known parameters, then the concept of dimensional analysis is quite helpful and therefore it gives a better results. Here we are going to adopt some of the advanced technologies, some of the methods for building the relation between the given parameters. That the methods of the dimensional analysis which we are going to discuss in the further on topics. And mathematical techniques used in this for research work and as well as for conduction of simulating the models or for the analysis purpose is also quite advantage for the dimensional analysis. So with this just a small brief introduction, now I am going to go ahead with the next topic. Basically the quantities whatever we are going to do for the consideration are basically divided into two parameters. One is the fundamental quantities and the other one is derived quantities. So basically the fundamental quantities are considered as mass, which is represented by m, length, and which is represented by L, time, which is represented by T, and temperature, which is represented as degrees centigrade. These are all called as fundamental quantities as they don't depend upon any of the parameters. And we can say that these are all independent parameters. And with these independent parameters, we are going to build the other parameters which are called as secondary parameters or derived parameters. And these are basically dependent parameters. And these dependent parameters may be expressed in terms of MLT. So here what we are going to say that the fundamental quantities and as well as the derived quantities are the one in which very essential for writing out the formula in terms of MLT of the given quantities. So here we can see the dimensions of a given object can be expressed in terms of linear quantities, say L, or with respect to the area, that is L square, and volume like L cube, which we can see in the figures here. And if you are going to take the time, T has a dimension which is the unit may be represented as the second. But if you take the velocity, which is a dependent quantity on the length and the time, which is expressed as L by T. So here that's what we had discussed previously, that the secondary or the derived quantities are those which are completely depending upon the primary or fundamental quantities. So what we are going to see the applications of these dimensional analysis. Basically, in the development of the equations for the fluid phenomena, like if you are going to take the continuity equation or Euler's equation or Bernoulli's equation of energy or the law of conservation of energy, wherever it is, the dimensional analysis applications can be found out. Next, conversion of system of one units to the other units. Basically, we have like a MK system and a CGS system or FPS system is also available. So, in order to convert that one type of the system to the other type of the system, depending upon the given requirements in the question, this dimensional analysis will be helpful. And if you want to reduce the number of variables, there also we are going to see the application of the dimensional analysis. And the basic important thing is that if you want to develop the hydraulic similitude, basically, for example, if you are going to consider the typical water distribution system, which is very large, which is consisting of network of pipes. But if you want to analyze it manually without the help of the software, then the chances of occurring the results with the errors are high. But in the case of the similitude process, just similitude in the sense of similarity, just we are duplicating the existing original structure, which is called as a prototype, and then we are going to build a model of it either in the reduced scale or enlarged scale, which is also called as a model, and that model can be easily simulated in the required software by giving the required inputs, and we can obtain the maximum number of outputs with less number of errors. So there the concept of the similitude, that is the similarity, is quite essential, and it is, we can say that this is also an application part of the dimensional analysis. Next, the important characteristic is that when we are going to design a pipeline, like which we are going to say that pressure drop per unit length, as we have discussed that in the case of the water distribution system, the pressure is the one which is an important parameter to be considered, and when we are going to fix the quantity of the pressure, the similitude is very much essential, and therefore the concept of dimensional analysis is going to be found its applications in the case of similitude process. Not only this water distribution system, in any of the cases, as we have discussed in the earlier classes regarding the applications of the fluid mechanics, like if you are going to take the wind tunnels, or if you are going to take the cars or automobiles, or if you are considering about that aeroplanes or aircraft structures, all these parameters require the similitude process, because we need to know the output or behavior of that structure under the actual conditions. So as we are unable to predict at all the times the exact output, the concept of similitude comes into the picture, and this concept of similitude is pure an application of the dimensional analysis. So here we can see some of the basic quantities like fundamental quantities and as well as the derived quantities with respect to their expressions of MLT. And also here on the right hand side, we can see that in FPS system also, that is the foot pound and second, that is the FPS system also, there we are going to express the same quantities in both the MK system and as well as the FPS system. Here are the basic, these quantities are very much essential, because whatever the problems we consider for the methods of analysis, they require here all the parameters, because without these knowing the dimensional parameters, we can't solve the problems. So this is very much essential in order to solve the problems, and therefore it is requested to concentrate the basic important parameters. In continuation, here we have some other parameters also. Next, the concept is the dimensional homogeneity. So the word itself says that homogeneous between what? The dimensional parameters of the given equation. Since it is an equation, it will be consisting the two terms, both on the left hand side as well as on the right hand side. So dimensional homogeneity means with respect to their dimensions, it is said that it should exhibit the same dimensional properties. For example, if you are going to say that x plus y is equal to z, this condition is going to be satisfied provided that x, y, z are dimensionally homogeneous. For example, if you are going to take like 1 plus 2 is equal to 3, it is possible since they are dimensionally homogeneous, they are numerical values. For example, if I am going to take x is the value which represents the mass, and y is the value which represents the density, and z I am expecting that it may be mass density. But is that possible? No. So here we can say that mass density, simply we can say it as a rho. But is that possible? No, because here x and y are having the different dimensional quantities, that is the mass and as well as the densities. So therefore, here it is not going to be say that even though if the x plus y is equal to z is the equation, provided if x, y and z should be individually having the same dimensions, then only it can be possible to say that the given equation is dimensionally homogeneous. For example, let us take the famous equation or the basic equation, that is the discharge equation, which we are going to use very frequently in our fluid mechanics, that is Q is equal to A into V. Now, if we are going to represent in terms of the dimensional parameters, this dimension discharge is meter cube per second. I am going to write down like L cube T to the power of -1, which is equal to, then A is represented as L square and T is meters per second. So I can write it down it as L T to the power of minus 1. So finally, if I am going to combine them, L cube T to the power of minus 1 is equal to again L cube T to the power of minus 1. So therefore what happens, this equation can be said like as dimensionally homogeneous. So here that is the concept of the dimensionally homogeneous. But there are some type of the equations which may not be satisfying the concept of the dimensionally homogeneous. So those equations we may call it as an non-dimensional homogeneous. So that such type of equations generally we come across upon the experimental results. Means whenever we know the quantities, and if you want to establish an empirical relation, and under that particular condition it may be applied. So such kind of equations are come across in very rare, but all the equations we consider in our general practice seems to be satisfying the condition of homogeneous. So we can say all the equations are mostly, for example, the discharge equation, the Bernoulli's equation, all these equations are called as a dimensionally homogeneous equation. See here you can see one of the example like the change in the total energy of the system, that is the delta E is represented as internal energy plus kinetic energy plus potential energy. That is delta in the sense it represents the change of energy. So if you are going to write down here the components which are represented in the above equation can be measurable in terms of the basic fundamental quantities and as well as the derived quantities also. But if we are going to analyze that equation dimensionally, it satisfies the values, the dimensional parameters in the LHS are equal to the dimensional parameters of RHS. So this equation can be called as dimensionally homogeneous. So whatever the equations 90% we come across are dimensionally homogeneous, except a few which we are going to prove under the experimental assumed conditions may be called as some non-dimensional homogeneous. So non-dimensional homogeneous, something it may looks like, for example, if you are going to take the delta E, the same equation, which is equal to, let us assume this whole term is X. So X plus some constant, I mean say we are assuming that X dash. So this X dash is might be a constant. But that X dash with the help of this X dash, what is going to be happen? It does not satisfy the condition of the dimensional homogeneity. So that is the concept of dimensional homogeneity, which is very, very essential. So here are the some cases which we are going to take the examples of the dimensional homogeneity also. So with this, we had come to a conclusion, the brief introduction regarding the dimensional analysis and their applications and the introduction part of the dimensional analysis. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.